student, hello. I have the pleasure to share with you a solution about an exercise about dampers. We have three systems, and each system is constituted by at least two cylinders and several dampers. And the question is calculate the dissipative function in each case. The first case, we have a system constituted by two coaxial cylinders. They are bounded, and we have attached two the dampers on them, alpha 1 and alpha 2. The dissipative function is d1 plus d2, and the first is half alpha 1 square of velocity of the point A where we have attached the damper. Here is the A, and the same thing for the second. Here is the point B. Now it comes to calculate the velocity of each point. In general, each point has two kinds of velocities. Translational velocity plus rotational one. But here in our particular case, you see that this little symbol means that the axe of rotation is fixed one, and it passes through G. And in this condition, we haven't translational velocity because this axis prevent the system to make a translation, and the system undergoes only the rotational motion. So V translational equal 0, and V rotational equal the formula of the calculation of rotational velocity, which is omega angular velocity cross product GA. Now, in this condition, when we have only one kind of velocity, we can avoid this expression and use easier than this. We can calculate directly the displacement S1 due to the rotational motion, and we derive it over the time. See the figure, you will find what is the displacement due to the rotation of the point A. It is the S1. Okay, the S1 is equal R1 theta, and by derivating we get R1 theta point. We will do the same thing for the point B, omega cross product GB, and we can avoid this expression because we have only one kind of velocity, and we proceed directly by calculating, by finding the displacement of the point B due to the rotational motion. On the figure, C2 S2 equal R2 theta, and by derivating we get this, and the main equation G is equal of this expression. Sorry. For the second system, we have three dampers, D1 plus D2 plus D3, and A is here, B is here, and G is the center of the mass. Now, without redoing the explanation, the previous explanation is the same, so we can proceed directly by derivating the displacement of the point A due to the rotation. See the figure, the point A, we have the displacement S1 is equal R1 theta, and the same thing for the point B. Look at the displacement is S2 is equal R2 theta. And for the point G, it hasn't displacement at all because it has neither translation nor rotation, because the axis of rotation passes through of it. The center of the mass doesn't. Velocity is equal 0. By replacing, we get this expression. Now, the last question is the last system is the rolling without slipping. Okay. D is D1 plus D2, 3, 4, and here are the points, and don't forget that the distance between A and G is equal little r, B is here. B is the point of contact of the cylinder with the floor, and G is the center of the mass, and G is the upper point on the cylinder. Now we can't avoid the use of this expression because we have two kinds of motions, yeah, and two kinds of velocities, translational and rotational one. And in order to better understand to understand well this motion of rolling without sleeping, I always told my students to decompose the motion into two motions, translational and rotational motion. So I start with a translational motion. Look at the figure. After translating, the point D comes here and it displaces with X, translational motion. The same thing for G, the same thing for X, and the same thing for B. As conclusion, all the points of all the cylinders, the Hurley cylinder, will translate with the same amount X, and so the same velocity, translational velocity they have. Okay. Now for rotational velocity, we have to use this translational velocity is in the direction of I if we choose this system of axis, of course. Now the rotational velocity, we have to use this expression. We can't avoid it because the rotational velocity can be in, for example, direction of G, of Z, of K. Okay, but in our case, particular case, you see the figure, all the point of interest, our interest are located on this axis, the vertical axis passing through G. Okay, so in this condition, for this axis or this point D, G, A, B, they have rotational velocity in the direction of I, all of them. So we can write that the VR is equal VRI. So you see that translational velocity and rotational velocity are in the same direction I. In this condition, only this condition, we can proceed as the VR, we can calculate it as the ds over dt. The s is the displacement of the point due to the rotational motion. And finally, we can write this expression. We will use this expression in order to express the velocity of a point. We start with point D. You see, the S due to the rotation, see the figure, is this one, S1. Theta, it's equal R theta. We replace and we get this. Now we need to find the X with respect to theta. Since we have the rolling without sleeping, you have to take it in by heart. X is equal R theta. And in order to be convinced, you see the figure, you see the axis, the final axis after the wholly translation and rotation of the point D. You see? And in the other side you see the theta, and here it is the S1 is the same. Okay, and you can see that the S1 equal X. Now when we replace, we get this expression. Now we use the same thing for G, d over dt, X plus S I. And you see for the G there isn't rotation, there is only translation, so the rotation is equal 0. Now it remains the point A and the point B. Look at, we use the expression, and the S is equal for the point A is equal minus R theta. You see the figure, S2, you see, and the direction of S2 and X, they are in the opposite direction. That's why we put minus R theta. Now the last point, VB, is we use also the expression. For the S, you see, it's S3. minus r theta. Okay, and since we have the rolling without slipping, x is equal r theta, so the final result is 0. The point B hasn't velocity. And here, between brackets, we can conclude that this point, it is this point, it is particular point, because this velocity equals 0. When the velocity equals 0, it means the real axis of rotation passes through this point, and you see that the point is instantaneous. It's displacing. So the conclusion here, the axis of rotation is instantaneous one. It changes every time. And by replacing in the main expression, we get this expression of D. I hope that it was clear, and I hope you good luck.